Good morning, students. Uh, Previous class we discussed on load and store multiple data items and load and store single data items. And today, we are going to discuss the new topic, swap instruction. This swap instruction is basically a special case of load and store instruction, and this is similar to the load and store instruction. Load was transferring the content of the memory to the register, and the store used to transfer the content of register to the memory location. But swap basically exchanges the content of memory location and the register. Remember, swap instruction can exchange the content of only memory location and a register. It cannot exchange the content of two registers or two memory locations. That is what is basically the swap instruction. If there is a need for you to exchange the contents of a memory location and a register, then you can go for using the swap instruction. So one important thing in the swap instruction is that it is an atomic instruction or an atomic operation. Swap instruction executes using this atomic operation principle. Now, what is that atomic operation? When the swap instruction is getting executed, it is not possible for any other instruction to perform either the read or the write operation on the memory location and the register that is currently being used by the swap instruction. That means until the swap instruction finishes its execution, it is not possible for any other instruction to make use of the memory location and the register that is currently being used by the swap instruction. That is the meaning of atomic operation. Now, what is the syntax of the swap instruction? The syntax of the swap instruction goes like this. So you have the mnemonic SWP and an optional B, because you can swap the bytes also from register to memory and register to memory to register. And optional condition is also, you can embed an optional condition also to the swap instruction. And next you have the destination register RD, and then the register RM, and the memory location. It basically comes with the three operands. We'll understand how these three operands are used for exchanging the content of the memory location and the register in a short while. Swap basically it swaps the word between memory and a register. Now when I mean a word, it is a 4-byte number here or a 32-bit number, and the swap operation is similar to the one which you have already studied in the previous semester, because most of you have learned how the swapping works, especially you used swapping while implementing the bubble sort logic, and this is what you had written there. Now what we are doing here is we are copying the 4 bytes of data from the memory location, whose address is held in the register Rn, to a temporary variable. Now we have this is what the register which is holding the address of the memory location, and from that memory location I'm copying 4 bytes of data to the temporary variable. Now the memory is copied to the temporary variable. Now I'm putting the value which is available in the register RM to this memory location, and the content of the memory location, which was assigned to temp, from the temp it is now being assigned to the destination register RD. This is how it is happening. And if I just want to explain here, simple, the content of the register RM goes to this memory location, and RN content goes to the register RD. So you have to remember this direction. RM goes here, and the content of this memory location goes to the register RD. And the another instruction is SWPB, which stands for the byte, similar to exactly same as this. Only thing is, instead of 4 bytes of data, now it will copy a single byte of data from memory to a register. You can exchange or swap a byte of data from memory to register or register to memory. And as I already told, the swap instruction, it cannot be interrupted by any other instruction, because the swap instruction is an atomic instruction or an atomic operation. When this is getting executed, so it holds the bus until it finishes its execution, and it is not possible for any other instruction to use the bus when the swap is getting executed. That means it is not possible for any other instruction to write to this memory location or to this register when swap instruction is being getting executed. So this is what the syntax and of the swap instruction is. So next what we have is an example on swapping. Now this is what the precondition I'm assuming before this instruction executes. So in this memory location, it's a 4-byte memory. It is a word what we are speaking with, and that is mem32, and the address is this 9000. I'm assuming that this memory address we have this is the value stored, and R0 is initialized to this, and in R1 I'm assuming I'm having 4 ones and 2 4 twos, and R2, this is what the address, this address I'm holding in the register R2. Now I'm calling the swap instruction, swap R0, R1 and R2. Now what will happen when I do this? R2 is holding this address, and what is there at this address? This is the value. So that value gets loaded into the register R0, and the value which is available in the register R1 gets loaded into the register into this memory location. Now R1 was holding 4 ones and 4 twos. Now that is what is stored into this memory location. You can observe R1 content is loaded here, and the content which is available here, that is 1 2 3 4 5 6 7 8, gets into the register R0. That is what is the post condition of this instruction executes successfully. This is what the result you are seeing. So memory is finally holding this value which was there in the register R1, and R0 is holding the value which was there in the memory location, and R1 again still remains the same, and R2 is still holding the same address. This is the example. Hope with this example you understood how the swap instruction works. Now I have another example too here, that this is basically to explain how the swap instruction holds the bus until the transaction is complete. Now to hold the bus until it finishes its execution, the swap instruction uses the concept of binary semaphores. So there's something called as binary semaphores, which will be studying again in the operating system. I don't know whether you have already studied these concepts in the operating system or not. So you have something called as counting semaphores and binding semaphores, which the operating system uses in order to grant permission to one instruction at a time for using the resource. Now I have a simple example here. Now semaphore, it's a memory location which can store either 0 or 1. Now what we are assuming here is we are using a binary semaphore. What is a binary semaphore? A binary semaphore is one which can store either 0 or 1. Now here I have written the address pointed to by the semaphore either contains the value 0 or 1. Now this is a memory location. What is the name given to the memory location in semaphore? And that memory location can store the value either 0 or 1. Now what I'm doing, so the current value of that memory location, I am moving it to the register R1, and R2 I am moving it with the 1, and I'm calling the swap instruction, swap R3, R2 and R1. Now R1, it is either 0 or 1, and in R2 I have 1. Now what will happen? R1 content will go here, and the content of this memory location either 0 or 1 goes to the register R3. Now I compare R3 with 1. Now if R3 gets the value 1, 1 minus 1 is 0. Now we have the 0 flag set to 1, and BEQ2 spin. It goes back to spin. That means that this loop gets repeated until the value which is stored at the semaphore memory location is 1 1. That means if the semaphore value, the current value of the semaphore is 1, the resource what the process is looking for is currently held by some other process. I have written here, if the current value of the semaphore is 1, the resource is currently being used by the other process. That is the reason when I take the value at this memory location to the register R3 and I compare it with 1 minus 1 is 0, that means R3 value is 1. Now it goes back to this pin. It spins here itself until the value at this particular memory location is 1. What that 1 value is indicating is, so the resource is currently being used by the other process, and the process which is waiting to use this resource, trying to use this resource, has to wait until that other process releases. Now we'll see what if the current value of the semaphore is 0. If I assume this current value of the semaphore is 0, this value is 0, the resource is currently available or it's not being used by any of the process. That means if the semaphore value is 0, let us assume the semaphore value is 0, that means the resource is not currently being used by any of the process. Now what goes to the register R1 is 0. Now what goes to the register R2 is 1. Now what I'm doing here, I'm trying to exchange now. From R2 I have 1, it goes to this memory location, and here I have 0, that goes to the register R3. Now R3 0 minus 1, they are not same, the condition is false, it will come out. That means now the resource is allowed to access, so the process is allowed to access the resource. So at the moment it comes out of this, and here it can access the resource. Otherwise, if the semaphore value, current value of the semaphore is 1, it will keep looping here itself until it becomes 0. So now you can just go through the one more statement what I have written here. The process that intends to use the resource will make the change, the semaphore from 0 to 1, will change the semaphore value from 0 to 1. If the current value of the semaphore is 0, now the process is allowed to access the resource, and before accessing the resource it will change the semaphore value from 0 to 1. Now the moment it is made 1, it is not possible for any other process to use this resource. What they will be doing, they will be spinning here itself, and the process that intends to release the resource will change the semaphore from 1 to 0. At the moment the process finishes using the resource and the resource is no longer required by it, it will release the resource by making the semaphore value from 1 to 0 again, and any next waiting process, the new process which is spinning in this loop, will get an opportunity to use the resource again. Hope you understood. So this is how this is a simple semaphore can be used in order to grant the permission for using the resource to one at a time. Now I have a simple example here for swapping for demonstrating the use of the swap instruction. So we will try to understand this. Now for R0 I am putting this value, and for R1 I am loading the address of this, and LDR R2 comma R1. What I am doing is I am loading the content of this memory location R1 to the register R2. Now R2 will get 222, and then LDR R1 is equal to D value. I am just loading this, and then store R2 to R1. Now R2 I have R2 I have content of this memory location R1, this 2222. Now that goes and sits into the memory location one second. R0 is loaded with this. R1 gets the C address of C value. Okay. From there 222 is getting loaded into the register R2, and then I'm loading the address of D value to this register R1, and store is opposite. I'm storing the content of register R2 to this memory location, R1 memory location. R1 is holding right now this address C value, and then we are calling the swap here, swap R3 comma R0 comma R1. R1 is holding the address of this, and R1 is holding the address of D value, and R0 is holding this value. And what happens, 1111 goes to this memory location. That is what is important for us. R0 is this value, 111 goes to this memory location, that is here, and 222 will come to the register R3. So we'll just execute this program and observe. Yeah, I think this. I'm copying this. Control V here. I'll save, compile, assemble, build, now then debug. Okay. Yeah. Observe now. To register R0, I'm taking 1111. Now R0 is loaded with 1111, and R1 I'm putting the value of address of C value, that is 222, that is 1C. If I go to the memory location 1C, so there I can see 2222, and then I'm loading the content present at this to the register R2. Now R2 should get 222. R2 is loaded with 222. Now to R1 I'm putting the address of D value. This it is 4 followed by 7 zeros. Let me open one more memory window. 4 followed by 70 is this, and that is empty right now. And what I'm doing now, the content available in R2, I'm storing it to this memory location. Now 2222 will get copied to this. 2222 is get copied to this, and then swap I'm calling. Now R0 I have 111, and R1, so which is the address, it has 222. Now what will happen? 111 will come to this memory location, and this 222 will go to the register R3. And what is the status of register R3 now? 000. The moment I press F11, you can observe. See, 111 is here, and 222 to the register R2. This is basically a simple example which I take in order to explain how this swapping works. And here I've assigned it to 222. That's not necessary. You can initialize it to 000 if you want. Now I will go back to a presentation and continue. So this is the example. Next is the software interrupts. SWI stands for software interrupt. And this we have already understood. Say I want to call the execution of a routine which is present inside the kernel, then we have to interrupt the processor. Now how do I interrupt the processor? You can always interrupt the processor by using the instruction SWI. And again, inside the kernel there are many functions which are present. Now when you're interrupting, you got to specifically mention which function inside the kernel you are calling. This causes the software interrupt exception, then provides a mechanism for application to call the operating system routines. This is what I told you. Inside the operating system there are many routines. Say for example, I want to read something from the keyboard, so then again you have to make your program interrupt the processor and call the routine which is present inside the kernel, which is responsible for reading a character from the keyboard. If I want to print something on the screen, even a single character or a string on the standard output, again you have to make your program raise a software interrupt along with a particular function number which is responsible for displaying the character or the string on the screen. Now what is the syntax of the software interrupt? So this is what the syntax, and the mnemonics is SWI, and you can observe that even for the software interrupt also you can embed an optional condition, and followed by that is one operand, that is software interrupt number. Now this is what I was telling. Inside the operating system there are many routines, and each routine is given a number. Now you got to specify which routine inside the operating system you're interested in calling. Now with this table we'll understand how the whole process happens. Now I have the mnemonic SWI, and it is a software interrupt. Now this is what happens. Now LR underscore SVC, this is a banked register. LR is a simple linked register which you already know, and you know R14 is reserved for this purpose, and R13 is stack pointer, and R15 is the program counter. LR under SVC, you know, that is the supervisory mode, is equal to address of the instruction following the SWI instruction. Say for example, inside your program you called SWI and some number, and address of the next instruction which you're writing here, that is assigned to LR underscore SVC. LR is a link register, because after the routine which is there inside the operating system finishes its execution, the control should return back. Now where it should return back? It should return back to the statement that you're writing after SWI with some number. And next, and the other thing that happens is the current program status register gets copied to this. Since the processor has the CPU before calling this instruction, it was executing in the user mode. Now it will change its mode from user to the supervisory mode. Now it's necessary for copying the current program status register to saved status program register underscore SVC. And PC is initialized to vector plus 8, and this I've already told you why interrupt vectors are told. And interrupt vectors, so there are many interrupts: reset interrupt, undefined, and SWI is also one among them. Now SW inside the interrupt vector table, it is found at an offset of 8 bytes. Now hence you got to take the address of the vector table, and to that you got to add 8 bytes, and that becomes the new PC, because after this is called, the next instruction to be executed is the instruction which is there inside the operating system routine. That is why PC is computed with a new address, that is vectors plus 8. Now I can show you this why it is vectors plus 8. Let me go back to previous slides. Yeah, I think it is there in the second PPT. Yeah, just a second, it is not in this, it is there in my second PPT. Now here if I go to this table, you can observe the software interrupt SWI. So within the interrupt vector table, it is present at an offset of 8 bytes. Hence let me go to the current slide. Hence it is vectors plus 8. Hope you understood. And then CPSR mode, it is changed to supervisory mode, and CPSRI is equal to 1. Mask the slow interrupts. So IRQ is slow interrupt request. Slow interrupt request is masked, and you are enabling the fast interrupts. Yeah, this is what I already told. When the processor executes an SWI instruction, it sets the program counter to offset 8 in the vector table. So vector plus 8 it is. So take the starting address of the vector table, to that you have to add 8. Why 8? You understood, because the SWI interrupt within the vector table, it is present at address 8 at an offset of 8 bytes from the beginning of the vector table. And the processor also changes the mode to SVC, that is supervisory mode, because when the processor wants to perform the execution of any of the subroutine which is there inside the kernel, the processor should change the mode from user to the supervisory mode. And each SWI instruction has an associated SWI number which is used to represent a particular function call or a feature. This is what I mentioned. Every SWI instruction has an associated number, because when you're writing an SWI, it should be followed by a number, and that number determines which function you're calling inside the operating system kernel. Now I have an example on the same. I'll show you. This is the example. Let me perform the execution of this now. Let me stop debugging. Yeah, before I execute, let me explain this program quickly. what this is doing. See, I have again here EQ is an assembler directive, one more assembler directive. It is something like equate. Now SW I have this is starting from the beginning, that means it is a label or a variable. SW write, I am equating it to 0 0 0 right now, and then entry, and then start as usual. Now this ADR, I think you're not familiar, now you'll understand this. ADR, this is load address. It is ADR stand. LDR, you know, LDR is load data and ADR is load address. R1 text. Now what is this text? Text is a memory location again. In text I have written this hello world 0A 0D and then 0 0. Hello world is my string and 0A is for line feed. So for the new line. In assembly, in all assembly level programming languages, now /n is say in C programming, to give a new line you used to write the /n, but in assembly programming it should be a combination of A and D. Now A is I'll just show you here. Now say I have written something, now I want to go to the new line. Now if I just remove D here and if I give only A, what will happen is that the cursor will be taken to the beginning of the same line. The cursor comes here. A is line feed and D is new line. Now if I skip A and if I give only D, now the cursor will come to the new line definitely, but not to the, it will not go to the beginning. It will not go to the beginning. It comes here. It comes here. Anything if you write after that, it goes from here and it's not going to start from this position. Now if I want to go to the new line, so 0D says go to the new. If the cursor is here, where it goes, if I skip this, if I skip 0A, if I delete 0A and give only 0D, if the cursor, I assume if it is here right now, it goes here, and